Assalamualaikum warahmatullahi wabarakatuh. Topik 3.1 Hydrodynamics Fluid Flow. Okay, this is list of reference that you might refer throughout this topic. Okay, so today we want to learn on the conservation of energy and also Bernoulli Equation. Okay, the learning outcome first is explain Bernoulli principle, another one energy equation, and then evaluate the problems related to Bernoulli and continuity equation. Okay, conservation of energy and Bernoulli equation. Okay, what is conservation of energy? Conservation of energy stated that energy cannot be destroyed and it can only be transformed or converted into different types of energy. So this is the three types of energy that involve in fluid flow, which is potential energy. Potential energy is due to the elevation Z. Okay, when there is an elevation, of course it has the potential energy. Okay, next is kinetic energy. Kinetic energy is occur due to velocity V. Okay, so we have the velocity. So when the fluid start moving, it can cause the kinetic energy. And then another one is pressure energy. Okay, why pressure energy happen? It is because the fluid flow actually contain energy. When the fluid move from one part to another part, it's bring together the energy. So we have the pressure energy. And another properties that involve in the elements of fluid here, we have mg. So mg is actually weight, and then we also have area, cross section area, A. Okay, so we have area and A upper, which is the change of area. Okay, this is how we calculate the three energy previously. So we have potential energy represented by PE. So PE is weight times the Z elevation. And then for kinetic energy, we have KE. KE involves mass times velocity square divided by 2. So this mass is actually can be calculated as the weight divided by the gravity. Okay, so therefore when we substitute the m as W over G, so we get the KE is W V squared over 2G. And then pressure energy as the amount of work needed to move the fluid, so represent by Fe. Okay, P here is the pressure times the area and times the D. Okay, D is actually the length. Okay, so this is actually the volume, so represent by V. Volume also can be calculated as weight divided by gamma. Gamma is the specific weight. Okay, therefore the formula for Fe is density pressure times weight divided by density times gravity. Okay, then we need to total the energy. So E equals to potential energy plus kinetic energy plus pressure energy. So we can bring the W to here so that we can cancel the W, the weight. So we determine the total energy per unit weight. So we have this formula. And finally, it can be represent the total energy as H. Okay, and then pressure energy, pressure head or pressure energy plus the velocity head or velocity energy, and also Z, the elevations. So you can see here all the units must be in meter. Okay, you must make sure that you can add the true energy in unit meter. Okay, let's go through on the static, dynamic and stagnation pressure. Okay, why this one is occur? It's when the kinetic energy and the potential energy converted into flow energy. Okay, what means by converted to flow energy? It is cause the pressure to change. Okay, when the pressure change, we need to change a little bit on the Bernoulli equation by multiply with the density. So this is what we get when we multiply the Bernoulli equation with the density. Okay, so the pressure head just now, it becoming the static pressure. Okay, the P is the static pressure, and then the kinetic energy or kinetic head tadi, dia jadi dynamic pressure. Okay, what is represented by dynamic pressure is when the pressure rise when the fluid in motion and it brought to stop isentropically. Okay, when it is stopped, so it involves the dynamic pressure. And then the potential energy just now becoming the hydrostatic pressure. Okay, so same as previously, we need to total all the pressure. So we total up the static pressure, dynamic pressure and also hydrostatic pressure. And then the total pressure along a streamline is constant. Then Bernoulli equation. What is Bernoulli stated? Bernoulli said that energy cannot be created nor destroyed, so it can only be transformed or converted into another form of energy. So in an ideal fluid where there is no viscosity means that the total energy E within a moving fluid must remain constant. And then the total energy at a point in a steady flow must be equal to the total energy at any point in the path of flow, provided there is no energy added or taken from the flow. So it means that energy 1 equals to energy 2. Okay, we cannot add another energy of that 3 energy: potential, kinetic and pressure energy. And also we cannot taken from it. Okay, then Bernoulli equation between 2 points. So just now we have E1 equals to E2. It also can be written as H1 equals to H2, which is represented by the head, because we need to answer in unit meter. So basically in unit meter, pressure in unit meter we represent by head, H. Okay, so here we have the potential energy Z and kinetic energy and also the pressure energy or pressure head. Okay, so this is the picture of 2 points. We have P1 and also P2. Okay, this is assumptions for Bernoulli equation of 2 points now. So velocity on the flow cross section is uniform. So we are actually taking average velocity, and the effect of viscous force are very small compared to the gravitational forces. So we assume that there is no losses of energy due to friction. So we are not consider any heat loss or any losses of energy. And then energy of flow is not converted into another form apart from kinetic, potential and pressure energies. Okay, so that one we assume that the energy of flow cannot convert to heat energy. So heat energy cannot. Only kinetic, potential and pressure energies. Okay, then kinetic energy correction factor. Okay, actual velocity of fluid particles depends on their position from the solid boundary. However, when we derive the Bernoulli equation, we are using the average velocity. Therefore, a correction must be made by introducing the kinetic energy correction factor. Okay, we consider a small elemental fluid mass dm. So dm is change of mass moving with velocity. So the true kinetic energy is given by this formula. So dm is change of mass times velocity squared divided by 2. And then the kinetic energy across the section per unit time can represent by this, because when we involve time it change to flow rate, mass flow rate. So we change to big M, capital M, which represent by mass flow rate. And then we need to integrating over the flow cross section to calculate for total kinetic energy. So we have, well, after we integrate, we have flow rate here, Q. And then we have change of area. So we have equation 1, density divided by 2, integrating velocity cube times change of area. Okay, then we are considering average velocity. So velocity used is actually velocity average. This is for equation 2. And then the true kinetic energy is equal to the average kinetic energy by multiply the kinetic energy correction factor. So we equalizing equation 1 and equation 2 times the correction factor. So we get this one as the correction factor. So actually the correction factor can determine the types of flow, either uniform, turbulence and laminar flow. Actually the kinetic energy correction factor are often ignored, or it always set as 1 in elementary analysis. So bila dia dah set as 1, bila kita darab dengan apa-apa pun dia akan dapat nombor yang sama. Okay, so we can consider or ignore it for corrections of kinetic energy. Okay, then 3.1.6.3 is energy loss and energy gain. Okay, in practice, a real fluid has no viscosity. So there will be friction within the flow, which also cause the energy losses. So energy losses can be incorporated as head loss, HL. So it is actually energy loss. And then we have turbine, due to turbine. So when the fluid flow of element have turbine, so it can has the heat loss from turbine. And then also we can have another energy gain from the pump. Okay, so you can see here, loss we add. When there is loss of energy, we add. When there is energy gain, we minus. Okay, because we calculate losses and gain at the end of equation. So we need to use this one, plus for head loss and minus for energy gain. Okay, so we cannot put the energy loss here. We only can put at the second equation, because we calculate at the last of system. Okay, then representations of energy changes in a fluid system. Okay, the changes of energy and its transformation from one form to another can be represented graphically. Okay, in a real fluid system, the total energy per unit weight just now will not remain constant unless energy is supplied to the system at some point by means of pump. Okay, energy itu tak akan kekal melainkan kita akan supply pump. Okay, energy adding, energy gain. It will gradually decrease in the direction of motion due to losses resulting from friction and from disturbance. Okay, disturbance ni include change of size of pipe and also maybe losses from the turbine, energy loss from the turbine. Okay, so this is the graphically that mentioned earlier. So we have loss, entry loss, HL. So here, of course, we have friction here because we have curve from above to below, and then we have pump here. So here we have energy gain. Okay, and then this one we have total energy line or total head. And then also we have hydraulic grade line HGL, and plus the elevation and also the pressure head. Okay, so we have also here contraction loss, and also here we have exit loss. Okay, for this one it's okay because you will learn more deeper in semester 5, where we need to do experiment and laboratory on this topic. Okay, graphical representation just now is actually useful to identify the section of pipeline which are under negative pressure or positive pressure. Okay, we can know the location of the pipeline and also the pressure in the flow section that lies above the HGL is negative, and the pressure that lies below the HGL is positive. And then flow of water under negative pressure may lead to cavitation and also flow separation. Okay, let's go through on the examples for problem solving related to conservations of energy and also Bernoulli equation. So here we have a pipe conveying water tappers from a cross-sectional area. So area is given by 0.5 meter square at point A, and we have different area at point B, which is pipe mengecil, and the pressure at point A is given by 120 kilopascal with the velocity of 2 meter per second. So here you can see the word assuming there is no energy losses. So we don't have the HL and also HT for turbine, and we also don't have energy gain because in this question they not mention on the supply of pump. So we need to determine the pressure at point B, which is 4 meter above the level of A. So the Z is 4 meter. Okay, so this is how we imagine the question. We have 2 points, and at point A is datum. So we have elevation at point B 4 meter. And then we also need to write all the given information. We have area A, we have pressure at A, and also velocity at A. And we don't know the pressure at B. So this is the Bernoulli equation that we need to use because we are measuring the pressure at 2 points. So this is pressure head, kinetic head, and also potential head. So we can substitute ZA as 0 because it is datum, and ZB is 4 meter above the datum. Okay, then we can use the equation of QA equals to QB for flow rate. Flow rate A equals to flow rate B, and then we can determine the VB. Okay, we can determine the velocity at B. So only we can substitute into this formula. So after we get the VB, we have one unknown only. So we have PB. One unknown for PB, so we can easily calculate what is the pressure at point B. Okay, then we have another example that involve a siphon system. So for siphon system, we have 3 points. We have point A, point B, and point C. So stated that it has uniform circular section. Diameter of the smaller tube is 70 mm diameter. So dia ada bend pipe with its crest of 1.6 meter. The siphon discharge into the atmosphere. So this one means that the C is discharged to atmosphere. What means by discharge to atmosphere is P equals to 0. And the levels of the siphon that discharge into the atmosphere is 3 meter. So we need to calculate the velocity at the discharge V, and given the absolute pressure head at the end of the siphon is 10 meter head, calculate the absolute pressure at the crest, and also mention here we neglect all the losses. Okay, so B is another conditions of siphon. Okay, so this is how we understand on the question. So we have point A. Point A is at the free water surface, and the velocity is taken as 0. So this one you must remember. From atmosphere is 0, to atmosphere is 0. So we have 0 of pressure here. Pressure at point A is 0, and pressure at point C also 0. Okay, for point B is at crest of the siphon, means the velocity is not 0, and the pressure acting is not pressure atmosphere. So B, pressure is not 0. So beside the pressure, we need to know about the velocity. So in the tank, the velocity is 0 because stagnant. Okay, the fluid flow only on the pipe. So this one we have the velocity for point B, and point C also we have the velocity. Okay, let's go through the solution for the siphon problem. So here, first thing first, you need to remember that you need to write the formula or the equation. So here, firstly, we compare the head for A and head for C. Okay, then this is how we write the Bernoulli equation. So you can also assume that PA and P pressure at C is 0, and we know that there is datum for the ZA, and also the velocity at point A is 0 because it is at the free surface, and then the elevation for C is 3. Okay, it is considered as negative because it located below the datum. Okay, and then we can calculate the VC. So we get the VC as 7.672. Okay, VB is equal to VC. So we can use the formula to calculate the Q. Q is area times velocity. So you get the Q as this one. Okay, and then we have pressure atmosphere. This is for question B. Okay, question A, we already determined the Q, flow rate. Okay, and then this is question for B. We need to consider that the pressure atmosphere is 10. Okay, we have 10 meter head. So we compare A to B, pressure for A and pressure for B. So we can calculate the pressure for B. Okay, elevation for B is 1.6. And then we get the pressure at B. Lastly, we can calculate the absolute pressure, where pressure atmosphere plus the gauge pressure. So we get the absolute pressure of this one. Okay, next examples for elevated water tank that drain to underground about 30 mm diameter of pipe, and the Q is given, the flow rate is given, and there is a head loss. So this one is different question because we need to consider the head loss. If the underground pipe is located 1.5 meter below ground level, so this one below the datum 1.5 meter, determine the water surface elevation in the tank. So we need to find the elevation here, elevations of the tank. So we solve this question using Bernoulli equation, where head at point 1 is equals to head at point 2. So pressure 1 equals to pressure at point 2, where it is pressure atmosphere. So I mentioned earlier, pressure from atmosphere and pressure to atmosphere is 0. And then velocity at 1 also you know that is 0 because it is inside the tank and it is stagnant and not moving. So V1 is 0. And then we can use equations to find the Q2. Q equals to AV. So Q2 is given by 0.2. So you can measure the diameter of pipe or area of pipe, no, not diameter, area of pipe, using pi d squared over 4. Diameter is given by 0.3, and you get this one as the velocity at point 2. And then of course we need to substitute all the information given, all the information that you have inside the Bernoulli equation. So here we can determine the Z1. Okay, don't forget to add the head loss. Head loss must be at the point 2. So head loss is plus tambah. So the head loss is 3. So you can get the Z1 is 1.91 meter. Okay, let's go through how the Bernoulli equation when there is two situations. So first is examples of for water discharge from a large tank. Okay, actually what is much different is on the pressure. So when the water discharge from a tank, the pressure at point 1 is 0, and pressure at point 2 also 0. Okay, so we can cancel the pressure. How about the velocity? Velocity in the tank is 0 because in the tank it is stagnant, and we have the velocity at point 2. Okay, for the Z1 we have the Z1. For Z2 we consider it as 0 because there is no elevation for the water discharge. So we can conclude the formula for Bernoulli equation for water discharge from a large tank is Z1 equals to V squared over 2G. Okay, this one is considered as approximately 0. So what left is Z1 and the velocity at point 2. Okay, then moving for another example, spraying water into the air. So what is the difference is the pressure. For spraying water into the air, the pressure is not 0. So we have pressure 1, but the velocity at point 1 is 0 because it start to going out from the pipe. So we consider V1 is 0, and then Z1 also 0. So we have pressure at point 1, pressure at point 2, and also the Z2. Okay, velocity at point 2 also consider 0 because we not measuring the velocity for the water jet. So this is the formula that we get after we can cancel the 0, the measurement for 0. We have pressure at point 1 equals to pressure at point 2, which is pressure atmosphere, plus the Z2. Okay, then question for try yourself. I need you to try yourself and check your answer with this one. Okay, so you need to try this question. So we have two questions for try yourself. You can try first and check your answer. If there are any question, you can ask directly. Okay, thank you.